Okay, so let's talk about 15.4, which is integration in polar, cylindrical, and spherical coordinates. Well, for the most part, talk about polar. So some of the ideas are similar, and in the other coordinates. So these are fairly standard alternative coordinates. As I mentioned before, this is when you have a lot of symmetry. So if you for example, if you have a charged particle, and so the charge as you feel it in space, it really depends on the distance to the particle. So this would be, for example, a great place for spherical coordinates, right? Well, for integration, this also makes sense. Either the function that you're integrating or the region that you're integrating might sort of be naturally described or easy to handle in different coordinates, right? And since it's fairly common to have some sort of a rotational symmetry, it's common to use polar, cylindrical, or spherical coordinates. Right, so let's start with polar. This is when I have we had x and y in regular Cartesian coordinates, and these are cosine theta, are sine theta. So we have r, which is now just a positive or non-negative quantity, and theta, where we really want to restrict theta to some interval of length 2 pi. For example, we could do 0 to 2 pi, or maybe another common one is maybe minus pi to pi, but really any interval of length 2 pi will do here. Those are sort of the standard ones that people take. And so where is this helpful? Well, this is maybe kind of a strange naming. So it's most helpful if you have a region that is a so-called polar rectangle, right? Which what does that mean, right? It really means that I have r is between two numbers. Maybe let me call them r1 and r2, right? And theta is between two numbers. So let's call it theta 1 and theta 2, right? So let's draw a couple of polar rectangles. So what does for example, what if r is between 1 and 2, and theta is between, let's do 0 and pi. Let's do pi over 2, right? What is this? Well, this is, if I draw it in the plane, it's this set, right? This is at 2, 1, 2, right? So the radius is between 1 and 2, and the angle that we make with the x-axis, positive x-axis, is between 0 and pi over 2, right? So we get this quarter of an annulus, basically, right? Now we could, another, this might sound even weirder, another polar rectangle. I mean, here it sort of almost looks like a rectangle that's been sort of twisted, but maybe the most common polar rectangle would be, I don't even have to state this, right? let's just say this, right? And theta is anything. So maybe theta is I could just let it be 0 to 2 pi, right? Something like that. And then what is this polar rectangle? Well, this polar rectangle is the inside of a circle, right? It's still sort of this rectangle that's been sort of twisted around, right? I mean, you can think of, if it's theta from 0 to 2 pi, this is sort of one side of the rectangle, and then this inside side is just all at one point. Then there's this side of the rectangle, and then there's the outside, right? So those are the sort of the four sides of the rectangle, right? And one of them just is squished to a single point. I mean, you can sort of think about it over here. If we move this side to the origin, right? So it gets squished, and then we extend all the way around, right? So a disk like this is a polar rectangle, right? Even though it doesn't look much like a rectangle, right? Oh well, that's the naming, right? So anytime you have a set that has this sort of a structure, it might be worth it to use polar coordinates to integrate, right? Now, to integrate, we really need to figure out what is that little delta A, right? We're doing this is a two-dimensional integral, so we're doing in two variables, so it's about area, right? So that little, in rectilinear coordinates, in Cartesian coordinates, what this was a little, actual rectangle. Here, what this little guy is, that's where the origin is. That's 0, 0. And this little rectangle is somewhere over here. And let me draw. Right, these would be lines where theta is constant. And let me make it. It would be really small, but let me make it big enough so that we can sort of see, right? And so this tiny little rectangle looks like this. All right. Now, as we move along these rays from the origin, that's where we move. That's where R, tells us where we are on the ray, right? This is where R is 0, and this is where R is maybe 1. This is where R is 2, or R is 3, and so on, right? R tells us the distance from the origin, right? So we start somewhere here. Maybe this is R, and this is R plus delta R. So this is maybe, let's call this delta R, right? It's the change in R. Whereas this whole thing, this is what R is, right? It's how far we are away from the origin. Now, this angle, right? That's delta theta. Now, delta theta is not exactly the length of this side, right? I mean, it's not even really a rectangle. But and the further out we are, right, for the same change in angle, right? If we're as we're going further and further away from the origin, the same angle is giving us, we have to travel more distance, right? Well, what is this distance, right? If we really traveled this thing, if we traveled this thing, really, what would it be? Well, if I travel along a circle of radius r, and I travel delta theta, in terms of angle, the actual distance I've covered is r times delta theta, right? This distance this distance in a curved, curved path is r times delta theta, right? So maybe let me go over here. But really, if we're here, if we're interested in just the distance between these 2 points, it's not quite r times delta theta, right? I mean, on a if this rectangle is really small, then you don't have to worry about the curvature, right? You don't have to worry about how curved this is. This is just like if you're on Earth, right? You don't really worry about the difference that it takes. You know, if you're going from, well, now you're not going anywhere, but you know, in a normal time, if you would be going from your house to the school, right, you wouldn't necessarily worry about the difference between the distance that's sort of straight through, just a straight line from your house to school, or along the surface of the Earth, right? Because you probably live close enough to your school that doesn't make much of a difference, right? That the Earth is a little curved as you're going from your house to the school. Plus, I mean, you're not actually going in a straight line to begin with, right? But even if the Earth was a perfectly round sphere and you went sort of the shortest distance that you could, it would still be different than the straight line distance. But if you live close enough, it's close enough, right? If you'd be going from let's say here to Australia, well, then going along, you know, the path that the plane takes, well, that's quite a bit longer than if you actually drove through the Earth in a straight line from here to Australia. So but that's a long distance. Here we're very, very nearby. So this even as a sort of a straight distance, we'll say this is approximately r times delta theta, right? And because we're really really being generous, it's also this distance is very close to this distance, right? I mean the difference in the it's really this distance is r plus delta r times the whole thing times sorry. I have allergies. It's just the right time to get allergies, right? Okay, so it's if you have r, so this distance would be maybe over here. It's this is gonna be, well, I'm saying approximately because I'm thinking the straight line distance. It's approximately r plus delta r times delta theta, but really that's approximately because delta r is really small, delta theta is really small. Delta r times delta theta, it's really, really tiny, right? Because it's really something really small times something really small, right? So if you think about if I have 0.01 times times 0.01, well, it's on an even much smaller order, right? I mean that's a really tiny number. It's 0.0001, right? It's really tiny. We can ignore that part of it, and this is also r approximately, as long as these rectangles are really small, and for integration they are really small. Okay, so the area delta A, it's not quite, but it's as long as the area is small, it's approximately. Well, I have this. I'll put the r first, and then I have delta r, delta theta, right? So I have the r times delta theta. That's the side of this. That's the length of this side of the rectangle, and the delta r as the side of this side of the rectangle, right? So we're basically thinking of this as becoming an actual rectangle, or really close to an actual rectangle, when delta theta and delta r are really, really, really small, right? And so this is telling us what this dA was, right? Because in integration, this this dA, that was sort of the limit of this you know, the infinitesimal version of this delta, and that's where all these approximations actually become equalities in the infinitesimal version. So this was in terms of Cartesian coordinates. This was dx dy, right? Or maybe dy dx, depending on which order that you were looking at it. But now, because of this r, this is going to become r dr d theta, right? Or maybe r d theta dr. You can change the order here. Maybe one way to sort of remember it is just think about it's pirates that like to integrate in polar, right? Because you know, that's what pirates say. You know, it's ardi theta, right? I mean, that was a Scottish pirate. All right, so let's try to let's do an example of this. So let's suppose, well, maybe let me write down sort of the general formula, and then let's do an example, right? So the general formula, if R is this polar rectangle, which is given by R between R1 and R2, and theta between theta 1 and theta 2, then the integral over R of f of x y dA, well, it is I'm going to write it as an iterated integral, and I'll put the r inside, so it's going to go from r1 to r2, and the theta outside, so theta 1 to theta 2. Then f, well, what is x in terms of r and theta? It's r cosine theta. Y is r sine theta, right? And then dA is r dr d theta. Now you have it as an iterated integral. You can sort of forget that this was polar. You just compute what this is, right? So let's do an example. Let's suppose that we have this half annulus where we're going to say r is between 1 and 2, and theta is between minus pi over 2 to pi over 2, right? So how does this look? This is this sort of set. I think I made it worse. It's this set, right? Going from 1 to 2. 1 to minus 2, right? It's this sort of set, right? And let's integrate. Let's suppose that I have, I want to integrate over r of x, y plus y squared, right? dA, right? Well, you just write down what it is, right? So let me write it down in this form exactly, right? So it's minus pi over 2 to pi over 2. R is going from 1 to 2, right? And then I have this is my f, and I just have to plug in the r cosine theta, r sine theta. So I have xy, so it's r cosine theta r sine theta, right? xy plus r so it's y squared, so sine theta squared r dr d theta. Actually, maybe something that just what I see on exams, quizzes, and all that is if people are missing these sort of parentheses when they're doing something like this, it's if you don't write the parentheses over here, it's really easy to forget that the r is squared as well, right? So, and it's plus if you forget the parentheses, then it means something completely different to begin with. But even if you sort of say, well, I'm going to remember, I don't have to write down parentheses. Write down parentheses. Parentheses don't kill you. It's it's actually very little extra writing, and it makes it much easier to follow what you're doing, and plus it makes you not write the wrong thing. Okay. So let's see what this is. So let's first let me still write it as this double integral, and now I'm gonna put the r, distribute that r inside, and I'm going to sort of put these together, right? So I have the first term, I'm going to write it as cosine theta sine theta, right, times r cubed, right, plus, and then I have the sort of same thing here, right? I'm going to have sine squared theta times r cubed, right, dr d theta. Now, what we could do is, well, maybe I could have done that already. What we could have done was, I have to write it again. 1 to 2. The integral from 1 to 2. What I could have written is, well, there's a, let me put that maybe r cubed over here, and then cosine theta sine theta, right, plus sine squared theta, right, dr d theta. And now we have our little not a cheat, but a little rule that how can we integrate these in a simpler way. What's underneath the integral is something in one variable times something in the other variable, right? As r cubed does not depend on theta, and this thing does not depend on r, right? So that means I could write it as a product of two integrals, 1 to 2 r cubed dr, right, and the integral from minus pi half to pi half cosine theta sine theta plus sine squared theta d theta, right? Now it's basically two calculus 1 integrals. That's maybe just for completeness. Let's do them. They're not that hard. We have to use a little bit of some trigonometric identity as well. Maybe not for the r r cubed dr. Let's just do them separately. So here we have this is well, let me just do this like this, or 1 to 2, right? So this is 2 to the 4th divided by 4 minus 1 to the 4th divided by 4. So this is what so there's a 4, you know, I can take out a 4 over here, right? So this is really 4 times 4, right? 2 squared times 2 squared, and you divide by 4. So this is 4 minus 1 quarter, so 3 and 3/4. Yeah, let me maybe even write it like this, right? Okay, so that's what this is, right? And 3/4. All right. So now, if for the other one, we have minus pi, right? And now we had cosine sine plus sine square. Well, cosine sine, I multiply that's 1/2 sine 2 theta, right? And sine squared is 1/2 minus 1/2 cosine 2 theta, right? All right. So now we just have to anti-differentiate that, right? So the antiderivative of sine is minus cosine, right? And so if I have a 2 here, so I will have to have a quarter, right? And then a minus cosine 2 theta, right? So when I differentiate this, the 2 will come out, right? The minus cosine will become sine. Okay, so that works. Over here I have 1/2 theta, right? And the antiderivative of cosine is the sine, and there's a 2 again, so a quarter sine 2 theta. And this is when theta goes from minus pi over 2 to pi over 2. So, right, so if we have, if I'm plugging in pi over 2 into the sine, that just disappears, right? Because pi over 2, I multiply by 2, so this is, I'm plugging in pi and minus pi, and sine is 0 at all multiples of pi. On the other hand, over here, cosine is -1 at minus pi and -1 at pi. So I'm getting -1s over here. Well, but that means I get the same value, right? And again, it disappears, right? So that's all gone, right? So this is gone. This is gone. So I have 1/2, and then it's pi half minus, so plus. Right. So I have a pi. So it's pi over 2. Yeah. Hey, unless I did a mistake somewhere, we have that this is pi over 2. This was 3 3/4. So if everything was done right, let's hope it was. I'll leave it up to you to to double check my work. This was 3 3/4 times pi over 2. Yeah, whatever it is, right? We have to simplify that anymore, right? That's just what it is, right? That's not too bad. It's if you think about how we would do it before, you know, in rectilinear coordinates, in the you'd have this sort of half annulus, and you'd really have to, you know, to do it, you really have to split it up into, well, at least two. You know, it's possible to split it up sort of vertically. Well, it's really three. This, and this. Or you could maybe split it up horizontally like this and compute this, and this. Either way, it would be kind of messy. It's much easier to do it this way as a sort of single integral, because it's a nice, you know, it's something that's very symmetric, right? Okay, so basically all it is plugging in the you know, figuring out what the rectangle is, you know, changing the dA to r dr d theta, and changing the x and y into r cosine theta, r sine theta, and integrating, right? Maybe just one very small example. How do we let's compute the area of a disk or a circle of radius. Let's do radius 1 for simplicity, right? Well, so we said this is a polar rectangle, right? It's a polar rectangle where r is between 0 and 1, and theta is between, let's say, 0 and 2 pi, right? So how do I write that? If this is the, let's call it D for disk. So what is the area of this disk? Well, it's just the integral of 1, right? So I'll just write it as the integral against the area measure, right? dA, right? 1 times dA. That's what this is. Well, let's write it out in terms of polar coordinates, right? I mean, if you wanted to do this, you know, in the sort of the calculus 2 way, right? It's sort of or maybe in terms of the, you know, rectilinear coordinates before, you know, you do this as a horizontally simple, vertically simple region, right? You'd have that square root of you know, 1 minus x squared, or square root of 1 minus y squared, right? It would be a mess, right? You'd have to do some trig substitution, blah blah blah, right? All that. Well, here let's not do that. Let's do it in polar coordinates. So r is between 0 and 1. Theta is between 0 and 2 pi. Okay. I have 1, the function, well, I'm not substituting anything, it's just 1, right? And dA becomes r dr d theta, right? So r comes with this. Now, this is really easy to compute. Let me just do it over here. What is this? The integral from 0 to 1 of r dr, that's just 1/2, right? And you can do it in terms of antiderivative, but you know, you'll get r squared divided by 2, right? And you plug in 1 and 0, 1/2 d theta, and that is just it's just a constant integrated from 0 to 2 pi, right? So this is just pi, right? Because it's 2 pi times 1/2 pi. Well, that's what we know it should be. It should be, you know, the area of a circle of radius r is pi r squared, right? In this case, you know, the radius is 1, so pi. Okay, there's no trig substitution, right? Of course, I mean, this is a, you know, very simple simple example, but yeah. Okay, so let's let's talk about cylindrical, because that's almost like almost like polar, except with that z in there, right? It's maybe harder to draw this little element, but it's basically, we have in the, if this was the xy plane and z is going up vertically, right? Then really that little element, well, it had this base, and right, it's really this little box over here, with where the base is the same as the in polar coordinates, right? So we have x is r cosine theta, y is r sine theta, and z is z, right? That's our change of coordinates. And over here, this is again this side of this. It's almost a box again, right? Not quite, but it's almost a box. This is my delta r. This side is my r. Well, approximately r delta theta, and this side is well, exactly the delta z, right? So here the delta v, our computing volume, is, well, approximately, it's approximately r delta theta delta z, right? So our dv, the volume element, is going to be r dr d theta dz, right? The thing that was dx dy dz, right? You can see that it's slightly different, right? We still have to add this r if we're doing things in cylindrical coordinates, right? So let's do some. Well, let me maybe write down the general formula, for sort of a typical region. So the easy region to describe is, suppose that W is given by let's say xy. The point xy is so in the xy plane is in some region, let's call it D, right? And whatever it is, it's some region in the plane, right? This is a region in the plane. Maybe I don't know if that's any better. There's a lot of light coming from the outside. This is worse, right? This is maybe slightly better. Okay, sorry about that. So this is the region in the plane, right? It's some region. Let me maybe draw it or try to draw it over here. We have some region D in the plane, and then we really have we're going to have a graph of two functions over here, and our W is going to be what's in between these two graphs, right? Maybe it's a little hard to draw, but basically it's given by, well, x is in D, and Z is between some alpha and some beta, right? Now this could be these could be given in X and Y, or maybe if we're in cylindrical coordinates, maybe it's alpha r theta, z beta r theta, right? So they're either functions of x and y or r and theta, depending on on how you set this up. So unfortunately, I don't have room to write the integral on that page, so I'll do it on the next page. So then we have the integral over w, right, of f x y z dv, right? This is going to be however you integrate over d, which is going to be in terms of well, either r theta or however you're doing it. So it's let me not do this in in cylindrical yet. This is alpha. Well, let me do this in xy, beta xy, and let's suppose that alpha and beta are functions of x and y. F x y z, right? D z d a, right? So that's one way to write it. Well, another way to write it is I rewrite this in terms of the polar coordinates, right? So maybe if D is of the form where let's say R is between R1 and R2, and let's say theta is between theta 1 and theta 2, and we said Z was between let's say alpha and beta, and let me not maybe put the variables in there. Then you would have a triple integral where you're going. Let's maybe put the let's make it r. Let's put the the dA on the outside, or so I'm gonna have dr, and I can r is as a function, so I can pull it inside the theta, right? That's the dA written in some form, and this is alpha beta r1 r2 and theta 1 theta 2, right? So I forgot to put down what I'm so in terms of cylindrical coordinates, r cosine theta, r sine theta, and z, right? And there's still that r, right? And you can again do this in various orders. So if alpha and beta were really depending on x and y, or r and theta, then you'd have to do that all the way inside, right? Just like we did over here, right? You'd have to have the dz is all the way inside. Now, if they're constant, if all of these are constants, then you can swap these two. But you might have also maybe the theta dependent on the r, or maybe vice versa. Maybe you had that the r was depending on theta. That's also possible, right? Depending on how you describe the region in which you're that you're integrating, right? And so you have to put that in the right order, right, afterwards, right? All right, but it's the point of writing it like this was that it's really the same thing as polar coordinates if you write it as if you can write it like this, right? Where the dA is it's really you're writing that as the polar coordinates. It's the r dr d theta. Okay, let's do an example. Let's suppose that W is cone. Well, how is it is going to be given? So it's going to be this cone with the tip at the origin. Z is going to be between 0 and 1, right? And the cone is well, let's just write it sort of the standard way that people write equation in rectangular coordinates. So let's suppose that this is the W is the thing that's given by this equation. Now this means that how can I describe this region? Well, I could describe this could be this is much easier to write as R, right? It's R squared. Well, R squared less than or equal to Z squared. Well, R is always positive, and Z on my region is also positive. So I could write it. I could describe it in cylindrical coordinates in a simpler way, and that's why we will integrate over cylindrical coordinates. And theta is whatever. Let's say 0 to 2 pi, right? Okay, and let's integrate. Let's suppose that what I want to integrate over W is let's do 4z e to the x squared plus y squared dv, right? This sort of nasty looking expression. And so we write it out in some iterated way, right? Well, since z is z and theta are really the ones that are given in terms of constants, so that's the ones I would put on the outside. Maybe you can put the z on the outside completely. It doesn't really matter. Either z or theta. So I can either start with theta or z. And let's put theta over here. Now r that definitely has to be underneath the integral for z. So for example, in the middle, it's going from 0 to z, right? And I have 4z e to the r r squared, right? And now dv, and the dv was r dr, then d theta dz, right? And now we can start integrating. This is now actually three, well, really just two functions. There's no theta, but you can think of there's a function 1 out here, which is a function of theta, and so I can rewrite it as a product because it's a function of z times a function of r, right? So I can rewrite it. Let me maybe right. I can pull out. Let's do this first, right? Let's see. I can pull out the theta, right? That's the thing that I want to. 2 pi the theta times. Now I have to write these as I cannot split these apart yet, just yet. Let me write it as 2z, and then an integral from 0 to z of 2 r e to the r squared dr. Okay, dz, somewhere dz. I forgot the dz, right? Okay, this guy, that's easy. That's 2 pi. All right. So that I'm done with, right? So now this thing, I have to compute this. Maybe. Well, let me go on a new page. Let's write it down. So this was I'm doing 0 to 1 to z, 0 to z, 2r e to the r squared dr dz, right? So really, this is it's going to be a function of z, really. So now let me copy this thing to z. Now let's do u substitution. U is r squared, right? And so du is 2r dr. Hey, that's nice, right? 2r dr is here, so it's e to the u du, and when r was 0, I had u was 0, right? When r is z, u is z squared, right? And the derivative of e to the u is e to the u. Sorry, that was a dz. So this is 0, 1 to z, and now I have e to the u. U is 0 to z squared dz, right? So this is equal to 0 to 1 to z, and then I have e to the z squared minus e to the 0 as 1, right? And so dz, hey, I'm gonna do the same substitution again, right? I have 0, 1 to z e to the z squared dz minus the integral from 0 to 1 to z dz, right? And well, now I'll just leave it up to you. This is was a good place to do left to student, because well, we just did just redo that. I mean, this is really the derivative of e to the z squared. Really, I could have done it without the u substitution, and so this is e minus 1, really, and over here, well, this is the derivative of z squared, so this is 1, so it's really, anyway, let me not spoil the fun. So, but you can almost do this in your head now. Okay, so that's that's polar and cylindrical, and we'll cover more next time.